this lecture, we are going to start a conversation regarding operational amplifiers, or op-amps. Amplifiers, op-amps for short. This is pretty important. I mean, this is amplifiers. From its name, you can know that it's amplifying signals. If you have a small signal and runs through an op-amp, it is supposed to be amplified. So your ADC is able to detect it and then being sent to a computer so you can store the data to somewhere. Okay. So this is being used as a front-end amplification tool in pretty much all these data acquisition platforms and sensors, electronic circuits, all these kind of things. It's pretty important. And so here are some questions I want to ask first. So you probably want to think about it before we get into the details. So first, why is it called operational? So in the old days, before the digital circuit was invented, people used the op-amps to add different voltage numbers or different voltage values to the output, so they can do some arithmetic operations using op-amps. But nowadays, we do very minimum of this kind of operations anymore because it's really not that accurate compared to the digital CPU, all these kind of units. But you know, this is a name came from very old days, but we are still using that in some of the circuits, but not as often as like 40 years ago. Okay, so that's what you need to know. And the symbol for an op-amp looks like this. It's a triangle shape and has two inputs and one power, one ground. So it doesn't have to be a ground, but that's the lowest potential in the circuit. You can treat it as the power rail and the ground rail, right? So it's called VD and VSS. This is V out. This is V1, V2, V1, which is being connected to the minus sign, the minus terminal of the op-amp. So this is called the inverting terminal. And this is a non-inverting terminal. Okay. And after that, you need to know one very important property of all these op-amps, which is called open loop gain. Open loop gain is the voltage gain, it's AV for short. And V out, if you have an op-amp like this, so V out equals to the voltage at the non-inverting terminal minus the voltage at the inverting terminal, which is V2 minus V1 times AV, which is open loop gain. That's V out. And normally, AV, or ideally, I should say ideally, AV is infinity, but in real life, it's just a very large number. It's not really infinity. So in that case, you can imagine that if this is a huge gain, a little tiny difference between the two terminals will give you a really high voltage output. But however, since you have a voltage limitation in the circuit, you know, for example, these two voltages, this is like 5 volts, this is 0 volts, for example, and that's a power supply. So nothing can go beyond that voltage, the top rail and bottom rail, right? Those two voltages. So it turns out that is like whenever there's a little tiny difference between the two terminals, and it's going to saturate the output. So it's going to either will be saturated at the VDD or VSS. So you are having a digital signal output. And we're going to give you some examples regarding that later on, but just let you know at the very beginning, so you know what's going on here. So if I short one of the terminals to ground, for example, like this, plus minus, this is V1, and if I short this one to ground, and V out equals to V1 minus 0 times AV, or let's say A, as a gain. So it's going to be AV1 for the output. If I have a different example like this, and this time I'm shorting V1, I'm shorting the non-inverting terminal, but having V1 here being connected to the inverting terminal. So V out this time equals to 0 minus V1 times A equals to minus AV1. Yeah, just let you know that the way to calculate the output from the open loop gain is just use a non-inverting terminal voltage minus inverting terminals voltage and times the open loop gain. All right. And since I just mentioned that, since you have a limitation for the top rail and bottom rail, they are limiting the output voltage. So even though you have a really huge gain here, which is normally 10 to the 6, like a million times, so you can imagine if you have a little tiny voltage difference between the two terminals, something like this, a little tiny signal difference, and V out will be equal to what, right? So for example, A equals to 10 to the 6, and let's say this is a VD, that's a voltage difference between these two terminals. If VD is 1 microvolt, what's the V out will be if the gain is 10 to the 6? So it's going to be 1 volt, which is fine, because you can have a power supply to be 5 volts and ground, which is 0 volts. So this is well in this range, and which is not a problem because it's going to be amplified properly without saturating the output. However, 1 microvolt is tiny, right? It's very easily the voltage difference will be in the millivolts range. So if you have 1 millivolt difference as a VD from the two terminals, you are going to get 1,000 volts output. And definitely none of these integrated circuits can handle that 1,000 volts voltage. And this you only have 5 volts as a maximum. So what's going to happen is if you have this, your V out is actually going to be 5 volts. That's the maximum voltage the power supply can offer. If you draw a curve like this, and if the x-axis is VD, and here is V out, okay, and if you are changing VD linearly until some point, your V out is not going to change anymore because it's going to be saturated at 5 volts. It's the same as you're decreasing VD to the negative direction, and there will be some point it's going to be saturated as well. So this will be VSS, which is the voltage over here. You have if this is ground, like this example, VL will never go below ground. It's going to be something like this. Depends on your VSS. Is that 0 or is a negative value? Okay, so determine your output voltage. So make sure you know this property of the op-amp. And because of this, if there is a signal and you have a reference voltage, that's a signal input. It's a signal, random signal like that. And there's a Vref, that's a reference voltage. And here's VL. And if I plot this VP, that's a positive, or V plus, V minus. If your VP is a signal like this, okay, and your VM, this is VP, this is VM, or Vref, is a signal like this, the Vout will be a digital signal. So for example, if we are looking at this range here, V Vm is larger than Vp. Vm is larger than Vp. So Vp minus Vm times A will be, if we ground it, as 5 volts. Okay, so the maximum voltage you can get from the VL will be 5 volts, and the minimum will be 0 volts. I mean, even though this is huge, right? But this times a little tiny difference over here. So we are talking about Vm is larger than Vp, so which means this will be negative, theoretically. But the negative number, like a negative 0.000001, for example, okay, times 10 to the 6, and you are going to get a large negative number, right? Pretty large negative number. This will not actually be reached in here because the lowest potential will be 0 volts. So this will be actually 0 volts. So during this time period, you are getting 0 volts. All right. On the other hand, during this period, Vp is larger than Vm, so it's going to saturate your output to the maximum voltage the power supply can offer. So it will jump to 5 volts until here, then 0 volts until here, then 5 volts, 0 volts, 5 volts. So you're actually getting a digital signal out of it. So a circuit like that, or the application of using this op-amp here, so this is called a comparator. Because it is comparing the two inputs. You know, whenever the VM, this input is larger than this input, you are getting a 0. If VP is larger than VM, you are getting a 1. So it's letting you know which one is larger by giving you a different signal. So it's a binary signal, either 1 or 0. There's no other, all these random values. So this is one very important concept you need to know for op-amp. And another property you need to know is the input-output resistance and the equivalent internal structure, what that looks like. An op-amp can be modeled like this. One input resistance and a voltage control voltage source, output resistance, and here's VL. That's a model for op-amp. V1, V2, that's an internal structure, but that's not the actual internal circuit of the op-amp. If you want to learn that in detail, you should take my Engineering 337 analog electronics. We are going to design an op-amp over there. But now we just look at the model of an op-amp. And that's the input RI, input resistance. This is a gain, A, VD. VD is the difference between these two inputs, right? That's a VD. And this is called RO. So for this model, for this op-amps model, which applies to all the op-amps we are going to use, RI ideally will be infinity. You need a huge input resistance for the op-amp. So the designer will figure that out. It's not your job. You just directly grab it and use it based on the curriculum here in the Forest College. And RO equals to 0. So you want this one to be as small as possible. So all the voltages will be delivered to the load instead of being consumed by self. If you think about this one is a voltage divider, so you hope all the voltages will be dropped over the load since it's trying to drive the load, but not the internal resistor inside the op-amp. And A should be infinity. Okay, so these are the 3 fundamental properties of a commercial op-amp you can buy from the market anywhere, or you're going to use in the lab in this class. So keep in mind, these are the properties of the op-amp. Okay, so now let's take a look at a very fundamental structure of the op-amps we are going to use. It's called inverting amplifier. So it looks like this. This is the feedback resistor called RF. This input resistor, we call it I1 or I, doesn't matter. And that's a V voltage input. And so there are several properties for this structure. The reason we need a feedback resistor over here compared to the open loop configuration like this, so there's nothing being connected between the VL and the input, any of the input terminals, is because we want to form a reasonable gain to amplify the voltage. We don't want this amplifier always amplify anything in the millions of times. So, we want to make it controllable. So if you have this combination, you can control the amplification. You can, for example, you can amplify the signal by 5 times, by twice, by 10 times instead of like 1 million always. Okay, so let's take a look at this one, how this works. It's very important. It can be confusing at the very beginning, but later on, you will be able to understand it. So the voltage is at these two terminals. Let's call this guy VM, since it's a V minus, it's VP. And there are several properties you need to know. First of all, VM equals to VP. So these two terminals are virtually shorted together. I mean, if you want to ask why, it's cannot be explained in one sentence or in one lecture. You have to take Engineering 337 analog electronics whenever you get a chance to understand this more. But I'm going to recommend you that for this class, do not think about that deep. If I tell you VM equals to VP, just remember it. That will make things way easier compared to others. Okay. And we know that here VP is ground, so it seems like VM is grounded as well, which is wrong. Okay. VP equals to 0 and grounded, but VM is not grounded. It is virtually grounded. Why? Why do we need this terminal to be virtually grounded instead of being grounded? We are saying like this equals to this, but only in terms of voltage, but not in terms of connection. So if you want to, for example, if we remove this guy, okay, remove this device in the circuit, so you are going to have something like this, R1, and going up, that's RF, and that's VL. So here's VP is grounded, right? I mean, is this one grounded as well? No, keep in mind, it's not grounded. They are virtually grounded. It's only sending this voltage to here. So you can, when you are doing the calculation, you can treat this guy as 0 volts if this is grounded. But they are not shorted, which is very important. Keep in mind, it's not grounded. It's just 0 volts, but it's not grounded, which can be confusing, but I recommend you remember it for now. And I have another question you may have as well. So the question is, why is this topology can amplify the voltage? Now, it's better to be very clear about it for now, because it can be very confusing. So the way I want to let you guys understand this is, I mean, I'm going to just take this out and only leave all the resistors over here. And let's take a look at that. What's really happening over there? This is the load, and that's oh, there's no resistor here. Sorry for that. So that's VL. That's RF. That's R1. That's V in. Here's the ground. All right. If we only draw a resistor like this without an op-amp, so this is a resistor network without an op-amp. What's going to happen over here? So here's V in, that's a V in. As one resistor, another resistor, then the load. So is there any chance that VL can be larger than V in? Think about it. Now I have another circuit. That's out, that's RL. That's the ground. However, this is a resistor network with an op-amp. And the difference will be because this does not have an op-amp, the voltage will be dropped continuously until the VL. So VL will never be larger than what? Than V in, right? Because you have a current flowing through the circuit until the ground, and so the voltages will be dropped once, twice, and third times, and fourth time. You are always getting a lower voltage here compared to V in. However, if you have an op-amp being connected into the circuit like this, so if you have an op-amp like this, all right, that's an inverting topology. This pin will be dragged to where? To 0 volts. It's a virtual ground because of this guy. So what's going to happen is you have a V in here, but I'm sorry, this point is going to force the voltage to be dropped towards the lowest potential possibly in the circuit, which is 0 volts. So it's going to force the voltage to be dropped drastically over here to 0 volts. And then what's going to happen is because this guy is has a higher voltage compared to 0, because 0 is the lowest potential in the circuit. So the current is going to flow in that direction as well. So what's actually happening is all these two terminals are flowing current into this node. And what's going to happen is VL can be or has a chance to be higher than V in. Depends on the ratio between RF and R1. Right? So it's going to drop to 0 and then start rising again to here. That's a function of the op-amp because it has the infinite open loop gain. So you can have these two terminals virtually short to each other. Whenever you have a 0 here, it's pretty close to 0 at the end of the other terminal. So you can possibly amplify the voltage at the VL. It still depends on the ratio of these two resistors. All right, that's how that works. Okay, so I have a question here, a really quick question. So do you have to have a feedback loop to amplify a signal? For example, I have a open loop configuration, in, out, right? And I have a resistor feeding back something. So this is V1, V2 here, VL. do you have to do it like this to amplify a signal? So the answer is no. Because this is also amplifying. It's just not amplifying as what you want this to be, because it's less controllable. You cannot configure the resistor ratio to try to change the gain, voltage gain of the circuit. On this one, you are able to control it. Okay. Another question. So why an feedback loop will make your two terminals virtually shorted over here, or why these two voltages are very close or pretty much the same? So it's because of the feedback loop. Remember the answer first before we get into the details. Okay, because you have a feedback, so these two voltages are similar. In here, it's not. You can apply a different voltage here and different voltage here. They are not necessarily to be equal or even close, right? But over here, whenever you apply a voltage here, these two terminals will have a really similar voltage appear here and here. Very interesting, right? So why this happens? So let's look at this circuit, EM, VP, because this terminal is being fed back from the output to the input terminal, or the same wire or branch. For example, we have a huge AV here, which is infinity, all right? For example, if this one is a little bit larger than 0, okay? Because here is 0, no doubt, right? VP is definitely 0 volts, it's ground. However, let's assume like VM is not 0, it's a little bit larger than 0. So it's going to be V plus 0 minus V plus times AV, which will be infinity times what? Times a tiny negative number, right? It will be like something lower than 0. And this will be a huge negative number because this is huge. And it's going to be a large negative number over here, appear as the output. So this potential will be really low. It won't get there, but it's trying to get to really low voltage. And because this is bridging these two terminals, and this is very low, this is trying to be higher than 0, then what's going to happen is it's going to draw current to V out because this is lower potential, and trying to adjust these two terminals to be the same. Until they are the same, it's going to stop this activity. So it seems like it's going to happen that way. In real life, it's probably not even happening in that way. It's just trying to go into that direction. But whenever it tries to start doing that kind of thing, it's done. It's already adjusted. Okay, so that's why the feedback loop in the op-amp determines the virtual connection between these two terminals. Okay, this can be confusing for now, but I hope you can understand it later. If you cannot, just try to remember this first. So I'm pretty sure in the future you will be able to understand this one in a better way. All right, this is everything for this lecture. I'm going to see you in the next video.